My name is Jose Antonio Brenes Carranza, and I am going to present a research that we have been working during the last few years. The title of this presentation is Use of Huge Transform and Homography for the Creation of Image Corpora for Smart Agriculture. And I was working with Professor Gabriela from the University of Costa Rica, the Professor Javier Fernández Pastor from the University of Alicante, and the Professor Jose Maria Cámara Zapata from the University Miguel Hernandez, and I am from the University of Costa Rica also. So I would like to start my presentation presenting our team. We are an interdisciplinary team from 3 distinct universities, as we mentioned previously. First, the Professor Gabriela Marin, and we are from the University of Costa Rica, here in Costa Rica, in the Central America, and we are computer scientists. Second, the Professor Fernandez Pastor is from the University of Alicante, Spain, and the Professor Fernandez Pastor is an industrial engineer and computer scientist also. Finally, Professor Cámara Zapata is from the University Miguel Hernandez at Spain, and he is an agronomist. In our team, we have other people who is collaborating with us in the distinct conducted researches from other areas like physics, architecture, electrical engineering, among others. We are an interdisciplinary team. So, well, now I will start with the presentation. This is the agenda for this presentation. First, I will start with a motivation about this research. Then I will talk about 2 important concepts that we take into account in this research that we consider. Next, I will introduce our proposal of system, considering the requirements of it and the setup that must be considered for the image capture. Following, I will talk about the algorithm we designed for the preprocessing of images. This algorithm considers various phases like the capture, preprocessing, and optionally labeling and classification of images. And next, I will present the results we obtained from 2 case studies. Finally, I will present the conclusions of this work and the future work. Okay. As I mentioned, I would like to start with a short motivation about why we work to support the agriculture sector. According to distinct international entities like World Bank and World Economic Forum, currently we are suffering an accelerated population growth, which is causing at the same time an increased demand for food. According to studies and projections made by these entities, by 2050, we will require about 50% more food than the amount produced today. These problems are increased by other problematics like pollution of land and water, because for farmers, every day it is more difficult to produce food in a specific land area. On the other hand, around the world, developing countries suffer the problem of accessing technology for agriculture due to um, its high costs. We also have low levels of education in Latin America countries and a real need for technical assistance. Here, we consider that we can support the productive sector from academy by creating low-cost technology for agriculture and by providing technical support for farmers. All of these actions with the goal of improving production processes and to increase the food production. So, in the last few years, working in this field, we detect 4 distinct areas in which we can support farmers. One of these areas is the creation of digital tools to manage pests and diseases in crops. A second area is related to support production activities by doing predictions like prediction of yields, climate forecast, weather forecast, etc. Thanks to the artificial intelligence boom, um, currently there are a lot of research in these two areas. However, to make advances in these areas, we depend on the quality and quantity of available data, which is very reduced. Although it is possible to get high quality datasets for agriculture, like datasets for disease detection in leaves, mainly of tomato crops, for example, it is very difficult to get datasets for the same activity for other crops. But if we plan to conduct a study to analyze diseases in stems or roots, for example, the available datasets are too reduced or inexistent. For this reason, we mentioned that there is a scarcity of public datasets for smart farming solutions. But at the same time, we consider that this is an opportunity to make research. It is possible to create new datasets to analyze all of the mentioned things, but it is expensive and require a lot of effort. Well, what were we doing in the last few years? We were working to support farming activities in controlled environments. This is because we found that to increase production and to reduce the amount of resources consumed and the land required for the production, the greenhouse controlled environment provides us all the things that we need for that. So this way, we have been working on greenhouses to improve production activities, combining low-cost technologies, expert knowledge from the agronomists, for example, and digital tools, mainly the creation of new solutions. We have worked in distant greenhouse in Costa Rica and Spain, mainly. This slide shows the distant equipment we have used for the deployment in the fields to get data directly from the crops. We use ever low-cost equipment to make it possible to small-scale farmers to access the technology. And we have tested our developed systems with distant crops like tomato, bell pepper, lettuce, beet, and cannabis. It is important to mention that we have been working on the creation of an integral platform to support monitoring, control, and alerts of production activities. And in the area of monitoring and alerts is where it is developed the research that I am going to present. So, okay, now I will talk about two important concepts or mathematical functions. First, the Hough transform is a technique originally developed to detect lines inside an image. But in our proposal of system, we require to detect circles, as I will mention in a few minutes. So for this reason, we use a variant of the Hough transform that is known as the Hough circles function, which is based on the Hough transform and enables to detect circles inside an image. Well, with this function, we can detect circles inside an image with distant sizes and noise levels, which is very good for us to process image of crops. On the other hand, we have the homography, that is a geometric transformation that maps points in one image to corresponding points in another, keeping the same center of the projection and the alignment of the elements in the image. Our proposal uses the homography function to rectify the captured image before cutting it into individual images. Basically, we use the homography function to get a rectified copy of the original captured image, like in this example. But what what is our proposal of system? Well, in this work, we propose to get an automated method to capture image datasets for smart farming AI applications by using the two mathematical functions that I recently introduced. The method includes capturing and pre-processing of images And we enable to adjust the time slots for the image capture, making it possible to get a large number of images. This enables us to generate a large volume image dataset for AI applications, avoiding the researchers to use augmentation techniques to get a larger dataset. In our proposal, we have some requirements. First, we need a Raspberry Pi 4 to manage the image capture and the pre-processing phase. Second, we require a camera, but we can use a low-cost camera like the Arducam 64 or the Raspberry Pi high-quality camera. And finally, we need adhesive color circular marks to delimit the work area. Okay, by using these materials, we can set up the scenario in which we will take the pictures. We have to fix first the camera to a position in which we can take pictures of the plants. We can adjust the camera if we need a zenithal like this, a zenithal image or a side image. The camera will be connected to the Raspberry Pi, which is in charge of manage the capture and pre-processing process. And finally, we must set the marks with the adhesive color stickers in the background of the scenario. Now, we use the Raspberry Pi to schedule the image capture and to pre-process the images. The pre-processing of the images takes several steps as shown in this image. We will take the original image and we do a cleaning process to eliminate all the pixels distinct to the color of the markers. Next, with the result image, we execute the Hough circle function to the marks in the image, these marks. And with this mark, we execute the homography function to align the resulting image, to align and rectify the image. Next, with the rectified image, we make a cutting task in which we divided the image in the several parts that contain individual plants. This way, we can obtain several images of individual plants from a unique image. Here we present the program that manages the capturing phase. Here it's important to point out that we use an Arducam for this test that enables to autofocus the sensor, the camera sensor before to take the image. And in this case, we name the resulting images considering the date and time. But we can adjust it. Now, this image shows the algorithm in charge of the pre-processing and cutting of the images. The algorithm starts by getting the number of rows and columns in which the image will be cut. Next, the huge circles and homography functions are executed. And this is the second part of the same algorithm. Here, the cutting phase is executed, and the resulting images are named according to the original image name and the corresponding row and column of the resulting image. A final but optional step is considered for integration of the image dataset. It is important to point out that we provide a first labeling of the images considering the position of the resulting image in the original, like this, the row and column. But if required, the dataset can be manually labeled, for example, considering another things like the presence of plant or no plant, or if the image contains a germination or not germination, so on. About the results obtained from the use of our proposed system, we conducted tests on a Cannabis Sativa crop inside a greenhouse. The tests were carried out at the University of Alicante from October 2022 to February 2023. We conducted two case studies. First, to analyze the germination of plants growing in seedbeds, and the second case study to modeling plants in different growing stages. In the first case study, we plan to determine the germination stage of Cannabis Sativa plants, but we have to consider some limitations. For example, there were no Cannabis Sativa datasets, fully datasets containing images of germinating plants. We found some dataset of other type of crops, but not for Cannabis Sativa. Germinated plants, in some cases, invade neighbor cells at ground. For example, in this case, the plant invade the neighbor, or in other cases, and a cell of the seedbed is invaded from another plant. And manual cutting of images causes bad samples, because if we did not the rectify phase, we have to make the manual coding, and we get very bad samples. And also the movements of camera difficult decoding process, because during the day with the variation of the temperature, the camera is moving in all moments, so we can get an image at the morning distinct for the image, for example, in the night or in the evening. By using the proposed method, we get more than 80,000 images of individual plants in different growing stages, like the shown in this image. The images has 224 by 224 pixel size. That is a size that is commonly used for AI applications, and we produce a clean dataset containing only preprocessed images. And with our dataset, with our proposal, we reduce the need for an augmentation technique of the dataset. In the second case study, we plan to determine the plant's stem width from an image. And here we also have some limitations. Again, we found that there were no image datasets of Cannabis Sativa plants. The stem width calculation required images captured at the same distance from camera, so it is necessary to set or to fix the camera in a position. And again, the manual coding of images causes bad samples, like the last case, and movements of camera difficult decoding processes. Here also during the day, the temperature variation causes movements of camera. In this case, by using our the proposed method, we can get about 1,440 images of individual plants in different growing stages, like the shown in the image. We can adjust the capturing period. In this case, like due to we are analyzing growing of the plants, we decide to only 3 images per day at 8 a.m., at 12 o'clock, and at 4 p.m. And also, again, we produce a clean dataset only containing pre-processed images, and we avoid also the use of augmentation techniques for the dataset. Okay, about the conclusion of this work, we can mention that the scarcity of dataset for training deep learning modules highlights the importance of creating initiatives to share and release public datasets. There are a lot of datasets that are created by distinct researchers, but the problem is that these datasets are not publicly available. So creating new high quality training datasets is necessary, but also is a very hard task, costly, expensive, effortly. It requires to guarantee that datasets accomplish size, resolution, and volume adequate for complex modules. because we have to process images that are similar or equal to get better results. And automation of the image capture process and its pre-processing can reduce the effort required to create these new data sets. Also, with the proposed method, we created two new datasets for training smart farming AI modules, in this case for Cannabis Sativa crop. It is possible to create new datasets while doing other activities. In this case, for example, the farmers can focus on the production process and not for the capture of the images. And it is possible to get partially labeled datasets. In our case, we label the images, the resulting images by row, by column, and also considering the species or the day, the time in which the picture is taken is took, but it's possible to get a partially labeled dataset, and then we can also manually label the dataset, the resulting data. In creating new training datasets, we consider that is an ever-evolving collaborative effort that must involve data scientists, researchers, engineers, in our case, farmers, agronomists, and other professionals from distinct areas. As a future work, we plan to use the proposed method for the creation of new datasets for other crops like tomato, bell pepper, and others. We are currently working on these other crops, but we plan to use this method to create datasets for those crops. And the proposed method outside the greenhouse, because we consider that greenhouse is a controlled environment, but it is possible to use the proposed method outside the greenhouse, but considering external conditions like light and weather conditions. And we plan to test the proposed method by using other type of reference marks in the background. We use circular marks, but we plan to use, I don't know, square marks, for example, to test if it is better. I would like to acknowledge the entities that support this research. First, the Research Center for the Communications and Information Technologies at the University of Costa Rica, and also the School of Computer Science and Informatics, also in Costa Rica. And this research is part of the Agro Next program, in which we are researching about Cannabis Sativa crops. And this study also has been supported by the MCIN from the European Union Next Generation EU in the Generalitat Valenciana. Thank you so much for your attention, and I can answer any questions.